Hey, it's Mr. Donahue again. This time we're going to take a look at 25.4 unsaturated hydrocarbons. So our objectives will be to name and describe the structures of alkenes, alkynes, and aromatic hydrocarbons, their isomers, and common reactions that they are involved in. All right, so review. Remember that unsaturated means it's not holding the maximum number of hydrogens possible because of the presence of multiple bonds. Like if I had ethene right here, we could break that multiple bond and then each carbon would be able to hold another hydrogen. That's why ethene is unsaturated. Same reason here, propine's unsaturated, and the same thing here, we got benzene unsaturated. It could hold more hydrogens. So alkenes, alkynes, and aromatics are going to be what we're looking at. So alkenes, you're going to end up with these things called geometric isomers. So it's the same formula, the same bonding, but different spatial arrangement of the groups. And I'll show you what I mean. Uh, Remember, the molecule cannot rotate around a pi bond, so its configuration is fixed. So remember sigma bonding, we got the nucleus and electrons, and then they're overlapping. And then these are free to rotate around, go around in a circle and rotate. But in pi bonding, you have those pi orbitals overlapping like so. And that means you can't really rotate around because they're bonding above and below. So they're not like stuck in the middle and able to spin around it like the sigma bondings. Pi bonds lock it into place. So let's take a look. We got some sigma bonds and you can spin right around it. You see I'm holding it in place and I'm spinning and I'm spinning and all the sigma bonds can spin. Whereas if I take a look at a pi bond and I try to do the same, the springs are representing the pi bonds and they're fixed, right? So I can like twist it a little bit, but I can't really spin it. It'll still spin around those sigma bonds. But that pi bond, its configuration is locked into place. Okay, so side by side comparison. Sigma can spin and double bonds cannot spin. So if I got a double or triple bond, it cannot spin, right? Cool. So geometric isomers. So if we take a look, there's two ways that things can be configured. We can get a cis isomer, which means that similar groups are both on the same side, top or bottom, in relation to the double bond. So if I take a look, the orange is on the same side of the double bond. They're both above it. And the yellows are on the same side of the double bond. They're both below it. So this would be cis. Cis means like the same. So it's on the same side of the double bond. Or it could be trans, where the similar groups are found on the opposite side of the double bond, right? So trans, it's going to be on opposite sides of the double bond. So you can see the orange, one's on top of the double bond and one's below it. Same with the yellow, one's below it and one's on top. So those are the two geometric isomers. So if I want to draw cis-2-butene, all right, well, I know butene is going to have 4 carbons. So 1, 2, 3, 4. And the cis is going to tell me that it is on the same side. So 2 tells me where the double bond is. Now the question is, where do those hydrogens go? Well, cis is going to tell me that they're on the same side. So it's going to be like H here and H here, and then the rest of the hydrogens on those other carbons. Whereas trans-2-butene is going to look like this. Double bond, and then H here and H there, and then the rest of the H's, right? So that hydrogens are on opposite sides. Now, I didn't do a really good job of drawing these because what's going to happen is like at the carbon double bond, remember these are going to be trigonal planar because of their hybridization and the shape that they're taking, which means that they're really going to look kind of like more like this shape. So for cis, it's going to look like this, and trans, it's going to look like this. Right? So they got different shapes. All right, alkynes. So alkynes are very reactive molecules. They're seldom found in nature. They're so reactive, and they are important intermediates in industrial processes. Let me go back real quick. The reason they're so reactive is because it's a triple bond. We got a whole bunch of electrons hanging out here, which makes it a pretty appetizing spot for something that needs electrons. So it's very reactive. All right, so aromatics. Carbon bonds in such a way in aromatic compounds to make a ring, which is also planar by making sigma and pi bonds. So this is an example of benzene. Benzene is an aromatic compound. So if we take a look, each one of these compounds, or each one of these carbons, are going to be sp2 hybridized, which tells me that it's going to have a trigonal planar shape. which means that this is going to be a flat molecule. And what's also interesting about these aromatics is that they generally are pretty stable. And the reason that they're stable is because of the delocalized pi bonding. So if you take a look here, you go, hey, why did the double bond happen there and not here? That's a great question. And it very well could. And whenever you can say that, what that means is you have resonance. I also have a structure where the double bonds occur at other places. So the double bond would be here, here, and here. And when that happens, all right, which structure is better? They're both equally good. You have resonance. So what that really means is what the molecule is actually going to look like is kind of in between both of those things. These electrons aren't stuck between these two carbons. They are moving around the whole thing. They're delocalized. And what you'll often see as a short handwriting for benzene is something that looks like this. You'll get that hexagon, and you'll get like a dotted circle in the middle, or sometimes they just do a full circle because it's saying those electrons are on that whole molecule. They're not just stuck in between these two carbons. So some of the chemistry, let's talk about it. The double and triple bonds increase the reactivity of a molecule, right? They have a concentration of electron density and makes those spots areas of interest for things I want to react. We have a lot of negative charge going on over here because there's a lot of electrons in between those two carbons. Two common chemical reactions that you're going to see are going to be addition, where one of the multiple bonds is broken and the atoms are added to the carbon backbone on both sides of the broken multiple bond, or substitution, which is basically what you probably think it is. An atom on the carbon backbone is replaced with a different one. So let's take a look. Addition reactions are going to be pretty common for alkenes and alkynes. So the two electrons in the pi bond are used to make bonds with new things. So what's happening is we're breaking this bond, and we're breaking that bond, and then we're attaching those things onto the molecule. That's how we add things. We're breaking a multiple bond and adding it. So if XY was H2, this process is called hydrogenation. And I'm sure you can probably guess why. Hydrogenation, right? You're adding hydrogen to it. So hydrogenation is an important thing in your probably everyday life, unfortunately. In order to get this to happen, you usually need a catalyst to get the reaction to occur. And a little bit more about hydrogenation. If you ever seen partially hydrogenated, some of those multiple bonds are broken and hydrogen is added to them. The reason they do this is because it increases the shelf life of the fats and stuff, so products can stay on the shelves longer. But during this process, double bonds are also broken and remade. So we have all of these multiple bond things, and in nature you tend to only really find cis double bonds. This means all those cis bonds can be broken and remade into trans bonds. So you can get trans fats. I don't know if you guys have heard of trans fats. Basically, you just altered the structure of the fat. You changed its shape, which means you've also changed its function. And the body, isn't used to getting trans fats. It doesn't do a good job of dealing with them. So here's a good video to check it out. They go into great detail. The Deal with Fat SciShow. It's on YouTube. Check it out. It goes into great detail about why trans fats is a problem. All right, so addition reaction mechanism. How is this happening? All right, well, the first thing that's happening is hydrogen is attracted to the electron density at the multiple bond. We have a lot of electrons here. Here I have another polar bond with hydrogen, so the hydrogen is going to be slightly positive. It's attracted to those electrons just because they're different charges. So what happens is, boom, hydrogen gets attracted to where those electrons are. Now, the electrons involved in the pi bond break, and they make new bonds with the hydrogen. So, boom, that bond breaks, makes a new bond with hydrogen, and when that happens, this bond that the hydrogen originally had is also going to break. So the bond between the hydrogen and the chlorine breaks, and the chloride becomes negatively charged. So, boom, that happens, and we get a negatively charged chlorine ion. And what also happened here when we broke that multiple bond is that carbon became positively charged because it lost electrons. So what's going to happen? Well, the chlorine is going to be attracted to that positively charged carbon, and they're going to make a bond. So the last step is the chlorine moves over and makes another bond with the carbon. And we just added a molecule to our alkene. And that's how addition works. All right, so aromatic reactions, generally, when you have an aromatic, you don't get addition, you get substitution. You may be asking, well, why? If it has double bonds, why can't we just break those and add more things? Well, the reason is because the aromatics have a really stable configuration. This is really stable because it has that resonance structure where its bonding is equivalent. So we got two really good Lewis structures. It becomes more stable. So adding it is going to be a problem because it doesn't want to break those multiple bonds. So instead, what you're going to see with aromatics is substitution. So basically, one of the hydrogens is replaced. So what's going to happen with substitution is, let's say I was trying to do, I'm reacting it with chlorine, right? And I got chlorine. Well, what's going to happen is one of those hydrogens is going to get replaced and the chlorine will get added onto it, and you're going to get like the same molecule, but one of the hydrogens is replaced with chlorine instead. Cool. So how do you describe where those things are? Say I did it once, okay, and I want to add another one. Say, all right, I add a chlorine here, and a second chlorine is going to go somewhere on this molecule. We have different ways of describing where they are in relation to each other. So when you get multiple substitutions, you can get different positions. Right next to it is what we call the ortho position. One more step away is the meta position, and on the opposite side of the benzene is called the para position. So you can get like, all right, if I had something like this and I had chlorine and chlorine, this could be ortho dichlorobenzene, right? The parent molecule is benzene. We have two chlorines, so that's saying I got two Cls, and the ortho is saying that they're right next to each other, right? And if I had chlorine over here instead, then that would be meta dichlorobenzene, and if instead I had it right here, then that would be para dichlorobenzene. But you guys ready for some organic jokes? I bet you are. Okay, so here's a good one. What do you call this? That is orthodox. And if you had this, what would it be? That would be a paradox. Oh man, I got like one more. Okay, what if I did this? Oh, I already messed it up. Whoops. That would be metaphysics. I know. Painful, right? Subjecting you to my humor. Anyway, so what can you say? Summarize. What can you say about geometric isomers, addition reactions, substitution reactions? What can you say about that? Summarize. All right? Put it in your own words. Make sense of it. All right, I hope you found that helpful, and I'll see you in class. Goodbye.